The objective of this video is to practice drawing the star of slots and calculating winding factor. We're not going to be introducing any new theory in this video, rather we're going to work through an example to practice drawing the star of slots and to show you firsthand how you can calculate winding factor. We're going to do this by considering an example machine with Q equals 12, P equals 1, and M equals 3. In the first part, I'd like you to sketch the slot locations, number the slots, and indicate the angular spacing between the slots. So if you want to be fancy, you can draw this as a complete stator showing teeth and slots, or you can draw this simply as a set of circles going around a rotor and number them. Press pause now, do the example, and press play when you're ready to resume. Okay, so we'll start by noting that our slots, we have 12 slots, Q equals 12, so there's 12 slots, and therefore the angular spacing between the slots is going to be 360 degrees divided by Q, or 2 pi divided by Q. So I've chosen to draw this, I've taken the simple way out, I've chosen to draw this as a set of circles surrounding my rotor. If I was being more precise, I would actually draw this as a stator lamination with slots and teeth, but I think we've done this enough in this class that you should be familiar with what I am referring to. This is the answer to part A. Now in part B, I want you to calculate the slots per pole per phase of this machine. Press pause now and press play when you're ready to resume. You should have found a value for your slots per pole per phase of 2. That is denoted as Q in the textbook, lowercase q. Capital Q is the total number of slots, lowercase q is the slots per pole per phase, and because lowercase q is an integer, this type of winding is called an integer slot winding or an integer slot machine. If Q had been a fraction, it would have been called a fractional slot winding. We'll be talking more about integer and fractional slot windings later in this unit. You should have the following diagram on your worksheet. So we start off by noting that the spacing between adjacent slots, the phasor spacing between adjacent slots, is going to be 30 degrees, or pi over 6. And then every 30 degrees going counterclockwise, or going clockwise, we labeled slot phasors. And it's important to notice the numbering of the phasors in our diagram up here, or the numbering of our slots in our diagram up here goes counterclockwise, where our phasor progression is clockwise. And this is because, again, this star of slots rotates in the counterclockwise direction. In the next part of this problem, I want you to suppose that phasors between negative 50 degrees and 10 degrees on your star of slots belong to the plus U coil groups. That is, these coil sides are positive when connected to our phase U winding, while phasors between 140 degrees and 200 degrees belong to minus U coil sides. That is, these coil sides are connected in the negative direction. Indicate which coil sides belong to the plus and minus V groupings and the plus and minus phase W groupings. So we can graphically show this, that these phasors over here in this range are plus U, and these phasors over here in this range are minus U. And what that means is that, remember, a coil consists of two coil sides. One coil side has a positive current, comes out of the page, another coil side has a negative current, goes into the page. So you have to have an incoming and a return path. It's important that we have two positive coil sides and two negative coil sides to represent two complete coils. And we've told you which of those coil sides belong to phase U. Now, I want you to figure out which coil sides belong to phase V and phase W. Press pause now, give it a try, and press play when you're ready to watch me do it. So we know that we want our phase windings to be identical, but rotated from each other by 120 degrees. And we want this to happen so that phase V lags phase U by 120 degrees, or 2 pi by 3. So that means that I'm going to pick this range here for plus V, because this lags the plus U grouping by 120 degrees. And then opposite of that is where I want to have my minus V groups. And then I want phase W to lag phase V by 120 degrees, or 2 pi by 3. So therefore, I want this to be plus W, and then on the opposite side, I want this to be minus W. So from this, we've now deduced what our complete winding layout looks like. We could sketch a winding schematic or draw a detailed stator diagram indicating which coil sides are current enters and leaves the page. We're not going to do that though. We're going to continue on with our winding factor calculations. Next, I want you to sketch the phase U phasor. I want you to draw the phase U phasor by summing the coil side phasors for our fundamental harmonic for V equals 1. So that is, go to your star of slots, extract the phase U phasors, and show how they add up to produce the complete phase U. Press pause and press play when you're ready for me to do this. You can see that I have sketched the individual coil sides in blue, and then I've sketched the total phase U phasor in red. And I've numbered these. I've indicated the slot phasors in these by just indicating the slot number that each phasor corresponds to. And up here I've told you how that maps. So U negative 7, 1 means that this is the phasor for coil side 7 connected in reverse direction. So it's been flipped 180 degrees because it belongs to the negative U grouping. And the harmonic V equals 1. Press pause now, give it a try, and press play when you're ready to watch me do it. So our coil pitch factor magnitude can be expressed like this. And in order to calculate this, we need to figure out what the value for gamma is and what the value for P is. So gamma is our coil pitch. It's how many degrees our coil spans. And I told you that all the coils have the same pitch. And we have two options for making that happen. We could connect coil side 1 to coil side 8 and coil side 2 to coil side 7. In that case, we'd have coils with a pitch of 150 degrees. Or we could connect coil side 1 to coil side 7 and coil side 2 to coil side 8. In that case, we'd have a pitch of 180 degrees. We're going to assume the following. We're going to assume that we have the coil pitch of 180 degrees, or pi radians. And in the problem statement, I told you what the value of P is, so we actually already know P. Alright, we're now set to calculate our winding pitch factors, our coil pitch factors. And we'll present this as a table. And you can see that our coil pitch factors have a value of 1 for all the odd harmonics and 0 for all the even harmonics. That means that our output voltage, our coils do not link any even harmonics in our flux density. So our output voltage cannot have even harmonics in it. It is simply not possible. We could have even harmonics present in our air gap field, but they will not create a voltage in our final winding because our final winding consists of all these coils connected together in series, and the coils do not link flux densities with an even number of harmonics. I'm now asking you to calculate the fundamental winding factor, that is Kw when V equals 1, and the fifth harmonic winding factor, that is Kw when V equals 5. Please go ahead and try this on your own, and then when you're ready, press the play button and you can watch me attempt to do this. And so you can see I'm taking the graphical approach. I've sketched the phasor for each of the coil sides with unity magnitude. And I can do this because all the coil sides have the same magnitude. And the value that I'm interested in is the magnitude of the total winding factor. And I've indicated that with this red arrow, where the magnitude is. And so I'll continue with this graphical approach. And so I've now found my fundamental winding factor, and I have a correction to make. When I was indicating the magnitude of the winding factors in red, this should have been labeled as 4 times kW is equal to this magnitude. Because remember, our winding factor is equal to the vector sum of our phasors divided by the algebraic sum. So if we normalize everything to a unity magnitude, and we've got 4 coil sides, it's going to be equal to the vector sum of all of our vectors, the unity magnitude, divided by 4. Because 4 times 1. So we can now do the same thing for kW5. And I'm going to back up a second with this, and I'm just going to sketch the phasors from the star of slots for the 5th harmonic. We've got our phasors from our star of slots for our fundamental up here, and if we multiply the spacing by 5, we can construct the 5th harmonic. And I'm only going to draw the phase U phasors, because we don't care about the rest for this. We're calculating the winding factor of phase U. And so phase U consists of phasors 1, 2, and 7 and 8. And phasors 1 and 2 are separated by 30 degrees. So the 5th harmonic is going to be 5 times 30 degrees. They're going to be separated by 150 degrees. Phasor 7 is separated from phasor 1, by 180 degrees. So the 5th harmonic phasor for slot 7 is going to be located at 5 times 180 degrees. And similarly for phasor 8. So we'll draw this down below. And then we'll draw the phasor sum, taking note of, again, the connection direction. And then we'll finally sketch this out as a right-handed triangle. And we now have our 5th harmonic winding factor. It's 0.26. So winding factors always have to be less than or equal to 1, and we want our fundamental winding factor to be the largest. That means that our fundamental frequency is the most dominant in our waveform. That's the frequency that we actually care about. In an ideal world, all the other winding factors would be 0. However, for practical machines, it's not possible, so we just want them to be smaller. And you can see that in this case, the 5th harmonic winding factor is quite a bit smaller than our fundamental. And you'll see that we zoomed in just on looking at winding factor for the fundamental and the 5th harmonic. And the reason that we did that is that when we looked at our pitch factors, we saw that the 2nd and the 4th harmonics didn't matter. The 3rd harmonic for a 3-phase machine actually doesn't matter either, because if you sum up your 3 phases that are displaced by 120 degrees, the 3rd harmonic doesn't contribute. So in summary, this video gave you an example of how to draw the star of slots and do basic winding factor calculations for individual harmonics. And we'll be developing this theory further in future videos.